Okay, so we will continue with our discussion on the Newton-Raphson method. I quickly derived the Newton-Raphson method on the blackboard by using a graphical interpretation. So we will go through the derivation a little more slowly, and then we will see the important points concerning the Newton-Raphson method. As is our practice, we will solve some problems using the Newton-Raphson method, first with one variable, and then we will go on to solve a two variable problem using Newton-Raphson method. In order to see the potency and the power of the method, it would be better if we take a problem which we have already solved using the method of successive substitution. Okay, so we may decide either on the fan and duct problem or the what is the other thing, the engine characteristics problem, and then we will see how, if we apply the Newton-Raphson method for multiple unknowns, whether it fares better or not. Okay, so Newton-Raphson method is basically a root extraction method. Why do we say it is a root extraction method? Because we are trying to set f of x equal to 0, we are trying to find the values of x at which f of x tends to a numerical 0, because these equations cannot be analytically solved. Invariably we encounter nonlinear equations. Okay, so if you look at the this is a plot of f of x versus x for a typical function whose roots we are seeking to obtain, right. As you all know, as you are all able to see, the root is here. Okay, so this is basically again an iterative technique. So we will start off from somewhere. I call this as xi. So this is xi corresponding to this, no, corresponding to this we have f of xi. The root is somewhere far off. How does this method work? We draw a tangent at xi, okay. Wherever this tangent intercepts the x axis, we call it as xi plus 1, the next iterate. Okay, so this is f of xi minus 0, f of xi minus 0, right. So this is you are able to see, Anand? Please change your place. All right. Now, what is the algorithm? F dash of xi is approximately equal to right. Now can call this as the algorithm. We can just call it as a Newton-Raphson formula. It is one of the most potent and powerful techniques for solving a single variable problem. You can extend it to multiple variables. So, it is a very powerful technique. As engineers, you must not leave this place without knowing the Newton-Raphson method. This you should never forget, xi plus 1 equal to xi minus f of xi divided by f dash of xi, alright. So, what happens? The next one is x of I plus 1. So, you can go here and draw a tangent. So, hopefully it will converge to this within a few iterations. The major difference between this method and the method of successive substitution is you are using information on the derivatives. Since you are using information of the derivatives, the convergence hopefully should be very fast, okay. But we cannot say that the convergence is always guaranteed. Why do I say that? Look at the formula and tell me what could be the possible pitfalls or limitations or shortcomings of the Newton-Raphson method. Okay, limitations. Let us not write the advantages, we are able to see the advantages. So, it uses information the first derivative, it should be fast, it should rapidly converge, all that. Let us see the limitations which are not so apparent, okay, upon first sight. So, if f dash of x and f dash of x equal to 0 for any iterate is a real disaster for the method. F double dash of x equal to 0 causes the solution to diverge. F dash of x need not even be 0. If it is very small also, this fellow will oscillate too much, okay, this fellow will shake too much, that is a problem. So, it depends on that f of x divided by f dash of x should be decent such that it is small compared to x of I, so that you get a new x of I plus 1, okay. So, sometimes causes the solution to diverge, sometimes gets trapped in local minima or maxima. Okay. So, for each of these we can take a particular example, and show when it converges slowly, when f of dash tends to 0 it becomes disaster and all that. But again please be reminded that this is not a course MA 401 numerical analysis or something, okay. So, we are looking at optimization. So, I am going to stop at a certain stage, and if those people are interested you can always look at some books on numerical analysis to get more ideas about this method. Now, how do we get this algorithm using Taylor series? This is a graphical depiction. It is possible for us to get the same algorithm using Taylor series expansion, okay. Shall we get the same thing using Taylor series? There is always confusion, right, whether it is Taylor series or Taylor's series. that is Taylor apostrophe S or Taylor's series or Taylor's apostrophe. So there are several versions. I am using the plain vanilla simple Taylor series. So even if I make mistake, it's all right. I mean, so there is a level of simplicity associated with this Taylor series expansion. Now how do you do the Taylor series expansion of f of x of xi in the vicinity of xi? F of, can you proceed? F of yeah, can you proceed? Yeah, we will put, we can call it as x of I plus 1. Where xi is somewhere between xi and xi plus 1, right? This term plus higher order terms. Of course, when you are close to the true solution, it does not matter and all that. When xi and xi plus 1 are also close to the true solution x of x true, it does not matter. Now this becomes highly mathematically involved question, why it should be xi and where you want to evaluate the second derivative and so on, right. Let us not get into all those debates, right. Now if xi plus 1 and xi are sufficiently close and then or the second derivative is small, then we neglect the second and higher order terms. Neglecting yeah, does that lead to the same solution? What are we trying to make 0? Which is that we want to, you are trying to make 0, okay, 1. Minus, is there a minus? Okay, so using Taylor series expansion also we get the same result. Since both the graphical method and the Taylor series expansion give the same result, this must be the correct version of the algorithm, right. Okay, now we will start off with an example where the Newton-Raphson method is not powerful at all. Okay, so I will demonstrate to you the simple example that all is not too well. Everybody says all is well and all is well. All is not too well with the Newton-Raphson method. Let us take an example like this. So it has got to be problem number 8, is it? Good. Problem 9. Yeah.
Why is the first, the number one equation, why is it approximately equal?
It is not exactly equal. See, at some place we are putting exactly equal, but I want to remind you that we are chopping off so many terms, higher order terms.
No sir, f of dash of x is just a tangent.
No, when I use this, so graphical method is alright. You can put that. That's no problem. But here you have to be careful. Graphical method, there is no problem. Okay. So, but in the Taylor series expansion, I want you to remember that there are higher order terms which we neglect. Okay. So we have to talk about the convergence of this method, which involves some little more advanced math. So at 5 o'clock we will do it. Please be reminded that we have a class at 5 o'clock. Anyway, so we will be working on a lot of problems on Newton-Raphson method, so it should be fun. So problem number 9, determine the root of the equation, determine the root of the equation f of x equal to x to the power of 8 minus 1, x to the power of 8 over minus 1, it is not x to the power of 7. Evaluate the root of the equation f of x equal to x to the power of 8 minus 1 using the Newton-Raphson method with an initial guess of x equals 0.5, with an initial guess of x equals 0.5. Okay. So many people call it as x naught, initial guess is x naught. Answer is so obvious, but so it is very painful. What is the answer? 1. Okay, the elusive one. You start with 0.5, you see the fun, right? Shall we first write the algorithm? Before you begin to draw the tabular column, first write the algorithm. Xi plus 1 is equal to x minus bracket is not required, right? That is the algorithm, right? Yeah, you can. enough? Is equal to what happened? Does it go like that? Huh? I am not. I am just showing you how this function behaves. It is too much. So we have to now rig it. What do we do now? Not 3.2 is also bad, man. All values are decent or some indecent values are also there. Huh? So let us plot. Huh? Okay, so now tell me, why is this fellow misbehaving?
So the slope at the guess point is very different from slope at the solution.
Why are we getting that? So why do you think where did we start? Yeah, then it is okay, no? The slope? So the algorithm becomes very slow when it is like this, when it nicely converges if you have something like this, when it is moving very gently, in your initial guess is in that region, it takes forever for it to converge. Okay, should I put xi plus 1 xi and all that and show you too? No need, right? Okay, now we will. So the solution is of course x25 or x30. What is the x24 is what is the value of x24? So we will have to necessarily do it because this stuff is going outside, right? Now we'll just say 1, 2, 3 and we will go to 26, huh? In the interest of time. Point 5 leads to, huh? Is it correct or? Please be reminded that we have to fill it up, right? I have the freedom not to, but you guys have to fill it, huh? Yeah, now 20, 24. Yeah, what is the value?
1.0000.
Okay, so it's slowly converging. So all the big talk about Newton-Raphson method because it's using f dash of x very powerful and all that, it's not really, it doesn't cup, but it the convergence is very slow. Now let us work out a problem in which the Newton-Raphson method really works. Okay, problem number 10. Use the Newton-Raphson method. Use the Newton-Raphson method. Use the Newton-Raphson method. Use the Newton-Raphson method to determine the first positive root. Use the Newton-Raphson method to determine the first positive root of the equation f of x equal to x minus 2 sin x, where x is in radians. F of x equal to x minus 2 sin x, where x is in radians, starting guess x equal to 2 radians, starting guess x equal to 2 radians, x naught. So what is the algorithm? One minus 2 cos xi, right? Right? So I will plot this. Enough? This I have just shown the graphical variation of the two functions f of x equal to x and f of x equal to 2 sin x. So the solution is about 1.895, correct? Solution is x equal to 1.895. So which is the sinusoidal function here? What happened to the other one? Huh? It's still there? Yeah, so you can see exactly with the L01 is the difference between the two, that is actually f of x. You can see where f of x becomes 0. So I asked you to get the first positive root, it will also have negative roots, right? F of x equal to x will keep on going on the other side also, it will also have negative roots. So it is pertinent, it is imperative that I tell you whether you want whether I want the first positive root or whatever, okay. So if you work out the algorithm, if you work out the steps, what is xi plus 1? What is the so fast, huh? Absolutely fast, there is no comparison with the successive substitution, okay. So generally if you are in the right region, your initial guess is in the right region and this function is not slowly changing, f of x is not slowly changing with x, there is a good chance that you will get what do you say, you can get a very quick and fast convergence. Now please retry this problem with an initial guess of 1 radian, okay. So 10b, 10a initial guess is, yeah, if you go to 1.895 what do you get here? 895. So 10b will be x naught equal to 1 radian. I have also shown it on, I have shown it graphically. Now when you work out the parts A and part B, part A we started with 2 radians, it converged, part B you are starting with 1 radian, you are going to tell me whether it is converged or not. Then you look at the graph and then you will have your own understanding as to why it worked for some case, one case, and it does not work for the other case, huh? 10 steps, you are doing it in the calci, huh? When you start with 1, what is the next one? Minus 7 point, somewhere it goes, and then totally off, it comes back, it comes back. Now graphically explain what is the difference between starting at 1 and what happens when you what happens f dash of x at 1? What is f dash of x at 1? Close to 0. I told you when it is close to 0 it is a disaster for the algorithm. Okay, if it is close to 0 then suddenly from 1 it swings to, is it minus 7.5 or plus 7. It swings to minus 7.55, from there it swings to some other value, eventually it converges, but it takes a, okay. So that is why the initial guess is very important. So they will, people will say then there is some kind of cheating involved. If initial guess is so important, that is, if you know what the initial guess is then you already know the answer or something. But I think we can't call it as cheating, because oftentimes in engineering a mathematician can argue anyway, I do not have any idea and all that, but as an engineer you have a good idea of what is the approximate range in which you expect a solution. So therefore in optimization problems, if this involves a maximization or minimization of a particular function, leave the, for the time being forget that we are trying to seek a roots to a particular equation. Suppose you are trying to maximize or minimize, in that case you are using a technique which is similar to the Newton-Raphson. You will use a, what is called a conjugate gradient or steepest ascent or steepest descent method, where you will use information on the derivative, first derivative. So if it is going to give trouble like this, if you start at the wrong value, then if it is going to oscillate left and right, and then it is going to become difficult for you, then one possibility is to have some other technique which will localize, I mean which will ensure that you give an initial guess in the proper region and you direct the solution such that you get accelerated convergence. How do you do that? So you can use an ant colony optimization or genetic algorithm or simulated annealing or some other technique, where we will see this in the later part of this course. Suppose you have got a function which is a f of x is a function of x1 and x2, you are trying to, so this is what is called the feasible space. That means all combinations of x1 and x2 will satisfy all the constraints to the problem. There will be a working solution to the problem, but if you have an objective function, each of which will not be equally desirable. Some will have a high value of y, some will have a low value of y, depending upon the context whether you want to maximize or minimize. Some are more desirable compared to the others. Now if you start with the initial guess value, suppose this is your optimum point. If you use a gradient method, suppose you start from here it may work, but if you suppose you start from here it may not work, but if you start from here it may work. So what you generally do in these cases is you use a global optimization search technique like genetic algorithm or simulated annealing, and then you identify a region where the solution, where you expect the solution to occur, right. Once you are in this region, then you fire your gradient method from anywhere, it will work, okay. Now you will ask me, sir, if I am able to converge to, if I know from this region I am able to reduce to this region using genetic algorithm, why not I proceed and converge? Genetic algorithm, usually these global optimization techniques are extremely slow, okay. So you initially use a global optimization technique to narrow down the region in which you expect a solution to occur, and then once you have hit upon that narrow region, then use a very powerful calculus based technique which uses information on first derivative, sometimes you can use information on the second derivative, Hessian and all that, and then you can narrow down your search. So such techniques are called hybrid optimization techniques. They become the norm now for multivariable optimization problems, nonlinear optimization problems involving several variables. People are increasingly trying to use this, okay.